Some administrative information. When we had guidance last week, sorry, guidance on Friday last week, the room F2 is terrible, awful. So I won't use it. I'll keep it just in case, but for now we will use the cafeteria outside here, second floor. We just use this mingle area. So sit, work with in groups around the tables, and then we can walk among you and answer any questions you might have. So for now, for the rest of the semester, we use the cafeteria. Sometimes they may have some arrangements here, some parties or I don't know. Then we can't use it. Hence, I will keep F2 just in case. So then if it's locked here, okay, then you have to go to F2 to get the guidance. Okay, that was just an administrative information. Any questions before we continue? It's okay. We are talking about ideal machines. We had transformers. That was a large T, and we had gyrators, a large G. The last example I showed you, that was a transformer, which then also acts as a transducer. Transducer, that means a coupling between different energy domains. The first example, that was a gear. So you had one wheel here, and then another wheel here, and then a chain around them. That is not a transducer. You go from one rotating system to another rotating system. So this is not a transducer. It's a transformer, yes, but not a transducer. The transducer, that was the second example. Then we went from fluid domain into mechanical back and forth motion, translatoric motion. That's a transducer. So the T here actually be a coupling between fluid domain and mechanical domain. Now, gyrators, they are quite rare. You don't find many examples. And well, you have one example, this prank by a French physicist. He took a very heavy flywheel inside a suitcase. So you can imagine if you have a rotating disc inside here with a small engine, then he isolated the suitcase so nobody could hear anything. Then you have a gyrator. And if you lift it up and you can walk and you can slide and you can bend it like this, no problem. Until you want to go around the corner. This suitcase will not be turned. If you try, what's going to happen? He will flip straight up in the air. As this poor porter experienced, and he said, or he screamed out, "The devil is inside the suitcase," and he threw it all away. So if you try it, you will have a real surprise. The suitcase won't turn; he will flip up. Just try it. You will have the same example if you take a bicycle wheel. And if you hold it in an, I don't have any round wheels here, no. No. Say here you have a bicycle wheel, axis here. Just look from the side. So he's rotating in this way, phi dot, rotating really fast. And now if you have this stiff axis where this wheel is rotating, and if you try to tilt it all of a sudden, what happens? Well, the wheel, he doesn't want to tilt. He will tilt your fingers in the opposite direction, or actually in the third direction. So it's really strange. Also, you can have, well, we can take that later, another example. You see these cool guys when they are using the bicycle downhill, they're moving fast and they don't put their hands on the steering wheel. They put their hands in the pockets. Cool guys. How do you make it turn when you don't use the hands on the steering wheel? You just lean over. That's the same effect. You just tilt this one and then he will rotate in another around this axis. He will start to rotate. So what you then could have done, if you want to play sort of a trick on these cool guys, on the front wheel you mount a plate, heavy plate, more heavy than the wheel itself, then attach with a gear, so that this plate he will rotate the opposite way than the wheel. And then when he wants to turn this, and he lean over, and then the bicycle will turn the other way. Big surprise. Just try it. It's like people, they think they know how a bike works. So yes, everybody knows that you just lean over and then it turns. And if you think you know how to use a bike, do the following. Instead of holding the steering wheel like this, hold it like this. Be careful. You have to learn how to ride a bike all over again. Not easy. Okay, a gyro, gyrator, will have the following coupling between F at 1 here and Q dot 1 here, G, and then on the other side we had F at 2, flow Q dot number 2. What is the coupling? Well, a gyrator, he actually has sort of a cross coupling. So the F at number 2 equals the flow number 1 multiplied with a G. F at number 1, well, he will be flow number 2 multiplied with G. So there you have the two equations. And you could use, say, the first one as a definition of a gyrator, then the other one will immediately pop up due to the fact that we should have no loss of power. So then if one is given, then you have the other one there. But this will now be the definition of a gyrator. These two equations. And as I said, we don't have many examples, so they are rather rare. If you use this bicycle wheel, and now if you look at it sort of from more directly on the side here, here is the wheel, here is the axis, like this. The wheel is turning with a constant rotational speed, say omega, constant. Then you take a string and you attach it to one end of this axis, and then you hold it in this string. Now what's going to happen? Of course, if you just had a wheel that didn't rotate, he will of course fall down. So the gravity mg acting like this, and then you have some length L here. The gravity will produce a torque, then you have a rotation around this point. So the entire system here will just flip over. Of course it will. But not if it's rotating. That's also a trick you could have done. If you now take a suitcase again and say, if I inside this suitcase in this direction had a rotating mass, rotated really fast, heavy mass, then I could have taken this suitcase and I could have put it like this on the table, and then I could drop it and the suitcase wouldn't fall down. It sort of looked like magic. What would happen is he would start to slowly rotate in this direction, depending on how fast I can get this wheel to spin. So that is a stabilizer for you. They use it on ships, passenger ships that shouldn't rock too much, so the passengers get sick. So they have some stabilizers like that, heavy flywheel that rotates. Then the boat doesn't like to really flip over. So what's happening here? This rotational, what should we call it? Phi dot. Rotational speed is close to 0. Strangely enough, we have a torque in this direction. The torque M equals the force times arm L. So yes, you have a torque. He really wants to rotate around this point, but no, he doesn't. Instead, he starts to rotate around this point, this axis. So he will slowly rotate around the string. So there actually you will get a rotation. Now let's see, what did I call him? Should be here somewhere. I actually called him phi dot, and this one, what should we call him? Phi dot 0 or something, because he's close to non-existence. So what do we get now? For this problem, I can give you sort of the answer before we continue. The value of G, it is given by the angular momentum of the wheel multiplied with the rotational speed, the constant rotational speed. So it's actually the spin of the bicycle wheel. So that is the value for the modulus of the gyrator G. The question now would be, find this rotational speed phi dot. How fast will he start to rotate in this direction when you let him go? Okay. So then we have the following, G and a bond like that. On sort of the input side, we have this torque around this point. So here I will have a torque M, that's my effort, number 1. Is then equal to arm multiplied with gravity mg. As the flow, that is this guy who is close to 0. So here I have almost nothing. He's close to 0. What do I get on the other side? Well, I get this rotational speed around this axis. I get a phi dot here. That's the one I want to find. Phi dot. What about the effort up here? Well, I don't have any effort. Strangely enough, when you do the experiment, this velocity here, rotational velocity, is going to be constant. Meaning you don't have any torque acting in this direction at all. So the torque here is roughly 0. So there also you see this cross coupling. Effort 1, he is coupled with flow 2. Effort 2 is coupled with flow 1. So it's a cross. So yes, it's a coupling. 0 is coupled with 0. That's correct. It really doesn't tell us anything. But the other one, these two are coupled. So this one, effort number 1. So that is M equals L times mg should be equal to flow number 2 times g. Flow number 2, that is my phi dot multiplied with g. Hence, phi dot equals L mg over large G, the gyrator, which we were told had this value, the spin of the bicycle. So this is the answer to the problem. So the more heavy the wheel is, the faster he will go. Long arm, faster he will go. And well, if the spin is not too big, then it will actually be quite fast. But then if the spin is not big enough, then definitely the system will break. He will actually start to fall. You will have some friction in it anyway, so feel free to try and play around with it, but you need a certain spin to make this system work with roughly 0 motion here and a constant rotational speed in that direction. So that's a gyrator example for you. And now the question, is this a transducer? What was a transducer? Transducer, then you had a coupling, one energy domain to another one. Well, here, no. You have a rotational domain on one side, and you also have a rotational domain on the other side. So no, this gyrator here is not a transducer. Not a transducer. Any questions to this example? Okay. I don't have many examples with the gyrators, so that was one. The other one, important, that is a motor, a direct current motor. So you have a small toy motor, and then you have a battery, some volts, and then the motor will start to spin. So a battery, electrical motor, and then you will have a rotating axis like this. And here, rotating axis coupled with the voltage, the effort for this problem. So here, the electrical side, effort, that is how many volt. The flow, Q dot, that is how many ampere is running. And then we have actually a gyrator, because you see the coupling with such a device goes from the voltage down here to the speed. So it's a direct coupling between voltage and speed. So hence, yes, this is a gyrator. The torque here would now be given by the amount of ampere that actually goes through the motor. So that is a simple example of a gyrator, which we will going to use in some problems. Oh yes. What about this one? DC motor. Is this one a transducer or not? Oh yes, that's a transducer. You go from an electrical energy domain into a rotational mechanical domain. So yes, here, this is a transducer. And it's a gyrator because you have this strange cross-coupling, and it is a transducer. Transducer. So transformers, gyrators, definitions. Some books, they actually use, as it says here, GY or MGY. Same with a T, also meaning TY or MTY. We just use T or G in this course. We don't need to specify the modulus, whether it's a constant or not, whether it's a function or we don't care. So we just call him G for gyrators, T for transformers. Then it's up to the modeling, whether they are constants or function or whatever they are. Here are some examples. Mechanical transformers. Of course, direct coupling here between rotational speeds. So not a transducer, but a transformer. Pulleys and gears, chains, electric. And here, the classical example, go from a hydraulic system, fluid to mechanical. And then we have some pump system as well, displacement pumps. We'll come back to these examples later on. Here, spinning gyroscope. Strange examples, but mechanical devices as in gyrators. So the only example that I have that's important actually is this direct current motor. So that's really something you should be aware of. Okay. So then how to use these transformers. Well, we had this example here with the sprinkler load example. So we'll continue with that one now. Continuing sprinkler load example. Sprinkler example. Continued. So the problem was as follows. We had sort of a source That was then a power supply and a motor acting on a pump. Here we had a pump sucking up water from a reservoir and then push the water all the way up to a fire extinguish system in a high building. So that was the actual sort of a sketch of the real problem. And here we talked about say rotational speed versus torque. Here, rotational speed and torque. The source was a real source, not an ideal source. Ideal sources, there we could have a constant torque or constant flow, constant rotational speed. No, we don't have that. We had a real source, and the real source was given by a characteristics. So source, real, given by a characteristic curve. And this is sort of unquestionable. It's given from the vendor when you buy a motor, then this is given. For the resistance part, the load, well, we had the same diagram, phi dot and torque. Then it was a question of fluid resistance in the system and how high you wanted to lift up the water. So we had curves typically going something like this: 10th, 20th, and so 30th floor. So the load will be heavier and heavier the higher you want to lift the water, and also the resistance becomes more and more heavy the faster the water is running, the rotational speed of the pump. The actual system here was then very simple. That is the bond graph. So the source goes through a bond and hits the load, or the resistance if you like. And here we have torque and you have rotational speed, and finished. Now the sad part was when we put these two curves on top of each other, this actual curve here, it looked something like this. And then you see the problem. The source is not strong enough to start lifting water up to the 20th floor. The 10th floor, that was okay. Then you had a stable operating point here. Stable because if you slack down a little bit in rotational speed, then your power source is strong enough to accelerate it back. Or if you go too fast, then your source is not strong enough to continue that speed, he will fall back. So this is a stable operating point. But for the 20th and 30th floor, they will burn down to the ground if you have this coupling. So this is not a good solution. How to handle it? Now we use a transformer. We use a gear. So use a gear. Here is my source. That is a power supply and a motor with a rotating axis here, phi 1, torque 1. Then I have a small wheel here. Then down here I have another wheel, and then some a pulley between these two wheels. And then I will have a different rotational speed down here that enters into my pump, which sucks water up on the system. So the only change in the figure is this gear. Gear, that's this part. And here I will now have a different rotating speed, Q dot number 2, and a different torque, M number 2. And what's the coupling here? Well, clearly, when we now have it like this, it's a transformer. Because with a gear, if the one rotational speed is given, then you know the other one, as long as you know the radius, the two radiuses of these wheels. So yes, it is a transformer. So M1 here, and then Q dot number 1 here, M2 here, and Q dot number 2 here. Now we can sort of make a choice. Well, I have actually already chosen for you. You have this figure here where we have combined both our elements, the source and the load, in the same figure. So now I can do the following. I can say my source is now this one. I sort of join these two together and I call him, say, a source marked. How will he appear? Well, what was the coupling here? Well, for a transformer, this Q dot number 2, he was equal transformer multiplied with flow number 1. While this one, he must then be, that must now be 1 over T multiplied with torque number 1. So this is just now taken from the definition of a transformer. No colors? No. Okay. What should now my value for the transformer be if I want to have water all the way up until the 30th floor? What will the demand be? Well, I have to take this curve I have here for the motor, for the source, and I have to change this curve. So this is the real source. How can I change it? Well, I must change it such that this point, for instance, now can be lifted all the way up here above this one. So I sort of have to say roughly double it. Okay, it has to be doubled. The torque has to be doubled. The torque here should be twice the torque number 1. So this will imply, actually, just by looking at the figure, choose value for T roughly equals 1/2. How will this curve now look if I have chosen T of 1/2? The torque that I get here will be doubled. What about the rotational speed? They'll be halved. Of course, remember, we don't lose energy here, or we don't get some additional energy somewhere. Energy must be constant. So it's the same energy on both sides for the transformer. So yes, I can double the torque, but then I will half the rotational speed. So this curve, if I chose T equals 1/2, yes, he will go through this point. That's okay. What about this point? What happens with him? Well, the torque is 0. I have a certain rotational speed, but now the new speed is going to be half of what I had. So I will only get half if he will go through this point roughly. So this curve he will now look something like this. All the points on this curve, torques are doubled, rotational speed are halved. So he's going to look something like this. So this is now what I call S-marked. And there you see the solution to the problem. Choosing a proper value for the transformer, yes, I can get the water up and running all the way up to the 30th floor by choosing a T around 1/2. I pay a price because the amount of water that hits the 30th floor is going to be smaller than maybe what I wanted. But at least some water will come up, yes. So of course, if it's not enough, then you have to buy a stronger source. But if you are a cheap hotel owner, then you can do it like this. Just insert a gear, then you can sort of rescale this curve to this one. The equation, the coupling between them are given here. So this is sort of how we use a transformer, a gear, into the problem. So you have it here, and choosing a transformer 1/2 sort of hits it correctly. Actually, it's not a good one. If you zoom in, I think he really can't do the 30th floor. It looks like he starts a little bit under. So just for fun, I tested this with Matlab and used this, well, not interpolation, as I showed you before, the inter P1. That was one way you could get a continuous function out of a set of data. So here is only 4 points just to get this curve. Another way to deal with it is using polyfit. Now polyfit, that is quite neat. Say this function here, the source. For him, the m equals, say, coefficient a times phi dot square plus coefficient b times phi dot plus coefficient c. Then you have a second order polynomial for him. And yes, that can be done with polyfit. You just give him the original data and then specify the number of the polynomial you want to use. Here, second order is a fairly simple curve, so you shouldn't have any problems with that one. And then you can actually play around with such problems fairly easily. Now you have an analytical expression for this, torque. Then it's fairly easy to go further. You can have an analytical expression for, say, finding the maximum power here. What was the maximum power? Power equals torque times rotational speed, which now will be A multiplied with phi dot power 3 plus B phi dot power 2 plus C phi dot. So there you have the function for the power. When will he have a maximum? Well, you take the derivative with respect to the rotational speed and find something and demand this one equal to 0 and so on and so forth. So yes, you can play around with mathematical expressions if you choose polyfit. I'll put out this script for you so then you can see how the graphs are done. When you have the maximum power, you can produce this constant power curve. It went something like this. and well, actually not like that. The maximum power here must hit maximum power here. So it must be a curve going something like that. Remember, any point here on this original S curve has a corresponding point on this S marked curve. And they have the same power, so they belong to the same power curve. And the power curve, I was just setting him constant. Then you get a hyperbola. Torque goes like a constant number divided by the rotational speed. So that's just a hyperbola for you. Which is the one that I have drawn up here. And now, using a transformer, you can scale or transfer the source curve, the characteristic source curve, to a new one. So here I had to multiply with not 1/2 but 0.45 just to get the 30th floor up and running. So if you zoom in here, you should see, yes, you just make it, because if the load were to be higher than the actual torque you have on the motor will never start rotating. The pump will never start to run, and the motor probably will burn up. So I would say not 1/2 but 0.45. Okay, any questions to transformers, gyrators? Then we stop here.